Imagine finding out your company's entire database was stolen.
Oh, man.
Right. And the whole attack, like from the very first cracked password to the final data exfiltration, it took exactly 72 minutes.
Yeah, little less time than your lunch break.
Exactly. I mean, for decades, cybersecurity has been this, human speed game of cat and mouse.
Right.
There was a timeline, a beginning, a middle, and an end. But today, we are looking at this terrifying new reality. It's machine speed warfare, where that timeline doesn't just shrink, it completely collapses.
It really does.
Yeah.
I mean, it is the absolute definition of a paradigm shift.
Yeah.
We just aren't dealing with human limitations anymore, or, cognitive friction, or even just the physical time it takes to type out code.
Right, because we are entering an era where the attackers are algorithms, and, well, they don't need to sleep or take breaks.
No, they don't even pause to think.
So we are dedicating this entire deep dive today to a single landmark document. It is essentially rewriting the physics of digital defense for all of you listening.
It really is a foundational text.
Yeah, it's a July 2026 paper published by ENISA. That's the European Union Agency for Cybersecurity, for those who might not know.
Right.
And the title is ENISA's View on Cybersecurity in the Frontier AI Era. So we are going to treat this session today as like an expertly guided masterclass.
I love that approach.
Yeah. We'll walk through this text sequentially with you. You're the student, we're the instructors, and we're going to unpack the complex mechanics behind these new threats, one topic at a time.
Sounds perfect.
Yeah.
And, the central thesis of this ENISA document, it's pretty stark.
Yeah, it is.
They argue that frontier AI models are fundamentally challenging our traditional security paradigms because they are compressing the vulnerability management lifecycle and the attack chain to near zero.
Near zero. That is just wild.
It is. And the truly alarming variable here, the thing that changes the game, is the proliferation of open-weight models.
Okay, let's clarify that for everyone.
Sure. So open-weight models are AI systems where the underlying architecture and the weights are freely available.
So anyone can just download them.
Exactly. Anyone can download, modify, and run them locally. And ENISA projects that these open-weight models are going to reach cutting-edge, state-of-the-art capabilities within just 9 to 12 months from this report's publication.
Wait, 9 to 12 months?
Yeah.
Meaning anyone with, like, a decent server rack in their garage can spin up an AI that rivals the massive proprietary models built by the giant tech companies.
That's exactly what it means.
Right.
And when you hand those open-weight models to skilled security experts or, highly motivated malicious actors, they get results that are comparable to the most massive closed systems out there.
Wow.
Yeah, so the barrier to entry for world-class automated cyber warfare has essentially fallen to zero.
Okay, so whether you are a developer pushing code or a C-suite executive managing enterprise risk or just an everyday user wondering why your data keeps ending up on the dark web, you really need to understand the mechanics of what is happening here.
Absolutely. You cannot ignore this.
So we're going to structure this walkthrough sequentially based on the paper. First, we'll look at the collapse of the exploit timeline.
Right, the speed aspect.
Then we'll break down the 7 structural challenges this creates. After that, we'll explore the fundamental shifts required in software development. And finally, we will conclude with ENISA's directives for defenders, which is basically the survival playbook.
The actual actionable stuff, yeah.
Exactly.
Yeah.
So let's jump in. The executive summary introduces a phrase that honestly forces you to completely rethink threat modeling.
Oh, negative time to exploit.
Yes, negative time to exploit. Let's unpack the mechanics of that.
Sure.
Because historically, vulnerability management relies on a positive time to exploit.
Right.
Like a security researcher finds a flaw in some software, they quietly notify the vendor, and then the vendor takes days or weeks or even months to develop a patch.
Sometimes longer, unfortunately.
Yeah, true. Then they release the patch, and the race begins. Attackers try to reverse engineer it to hit systems that haven't updated yet. But the defender always had a head start, even if it was just a small one.
Right, and that head start, it was built on this concept of private discovery.
Okay, explain that.
Well, it assumed that finding a zero-day vulnerability, a flaw that the vendor doesn't even know about yet, was incredibly difficult.
It took work.
Exactly. It required specialized human intuition and a lot of labor. But negative time to exploit just obliterates that assumption.
Just wipes it out.
Yeah. It describes this new reality where attackers are using autonomous AI agents to discover vulnerabilities and generate working exploits before the software vendor even knows the flaw exists.
Let alone has time to think up a patch.
Exactly.
So the AI is just out there constantly probing, it's finding these zero-day flaws autonomously and weaponizing them right on the spot.
Yes, the friction of human-led research is just gone.
Wow.
I mean, turning a discovered vulnerability into a weaponized exploit, it used to be a human engineering project. It would take a team of hackers weeks to orchestrate.
Right, sitting in a dark room drinking energy drinks.
Yeah, exactly.
Yeah.
But now, it is just a machine-speed computational task.
And the statistics ENISA includes here are honestly staggering. They say attackers can now weaponize new vulnerabilities within 15 minutes of disclosure.
15 minutes?
Yeah. If a bug is published or if an AI discovers one in your environment, you have less time to fix it than it takes, like, to commute to work.
Remember, that 15-minute window is just for the weaponization part.
Right.
When we look at the entire life cycle of a breach, ENISA highlights industry research showing that the median time from initial access to actual data exfiltration has shrunk to just 72 minutes.
Okay, I want to push back on what this actually looks like in practice for you guys listening.
Wait for it.
72 minutes to get in, map the network, find the valuable data, bypass internal security, and extract it. Human defenders literally cannot type fast enough to stop that. So, I mean, are traditional security operations centers, like SOCs, where human analysts just stare at monitors waiting for alerts, are they fundamentally obsolete now?
Honestly, if a SOC relies purely on human analysts to manually correlate alerts and authorize responses, then yes, they are dangerously close to obsolescence.
That is wild.
It is. The report actually quotes CERT EU directly on this mechanism.
Oh, right, the EU's Computer Emergency Response Team.
Exactly. CERT EU notes that what makes this latest generation of models so lethal isn't just the sheer volume of vulnerabilities they discover.
Okay, what is it then?
It is their ability to chain findings together autonomously.
Okay, walk us through the mechanics of vulnerability chaining. Like, how does an AI do this differently than a human would?
Okay, so imagine a human hacker finds a low-level misconfiguration in a server.
Okay.
On its own, it might just allow them to see, say, what version of an operating system is running.
Pretty minor stuff.
Right. A human then has to manually cross-reference that operating system against known databases. They have to find a separate vulnerability for that specific OS, figure out how to gain a tiny bit of user privilege, and then, manually search for another flaw to escalate those privileges to an admin level.
It's a really slow, iterative process of trial and error.
Yeah.
Like a puzzle where the human has to find one piece at a time.
Exactly. But frontier AI doesn't work sequentially like that.
How so?
It reasons about application logic holistically. It can look at an environment and instantly simulate millions of combinations.
Oh, wow.
It realizes, like, hey, if I use this minor misconfiguration over here to expose a hidden file, and I feed the contents of that file into this slightly outdated plugin way over there, I can bypass the authentication entirely.
Just like that.
Just like that.
Nice.
It orchestrates entire autonomous attack campaigns. It moves from reconnaissance to lateral movement and exfiltration without ever needing a human to prompt it.
So it's producing these complex exploitation paths that previously required highly specialized human engineering. Exactly. It turns a list of theoretical isolated flaws into a fully autonomous working attack.
Right.
Which means the entire traditional process of defending a network is, well, it's just fundamentally too slow.
Way too slow.
And that transitions perfectly into the first of the 7 structural challenges ENISA outlines in the text, which is velocity asymmetry and the authority gap.
Yeah, this is where the technical reality crashes headfirst into corporate bureaucracy.
Oh, boy.
Because the primary latency, like the main thing slowing down defenses right now, it isn't technical anymore.
Right.
The computers can update fast enough. The bottleneck is procedural.
The authority gap.
Yeah.
I mean, in a normal enterprise environment, if the IT department wants to push a major update or, say, patch a critical database, they can't just press a button.
No way.
They have to go through a change advisory board, a CA.
The dreaded CAB.
Right. They have to propose the change, test the patch in a sandbox, get approvals from various department heads to ensure it won't trip anything, schedule downtime, usually at like 2 a.m. on a Sunday.
And human cybes simply cannot authorize interventions in the 15 to 72 minutes available to counter an autonomous AI exploit.
It's like a committee insisting on holding a formal parliamentary vote on whether to deploy an airbag while the car is currently midair during a crash.
That is the perfect analogy.
By the time someone seconds the motion, the vehicle has already hit the pavement.
Exactly. Which brings ENISA to a highly controversial but really necessary conclusion.
What's that?
Organizations must implement autonomous patching.
Oh, wow.
Yeah. The defensive AI must have the authority to detect a vulnerability and deploy a patch immediately without waiting for a human to sign off.
Okay, hold on. Because if I am a C-suite executive or a lead systems architect listening to this, the idea of an AI blindly altering code on my company's critical servers without human review is terrifying.
Oh, it's deeply uncomfortable.
Right. I mean, we've seen massive global IT outages caused by faulty updates that were pushed automatically.
We have.
So how is automated patching an acceptable risk? Aren't we just guaranteeing that the AI will accidentally take down our own network?
Well, it is a brutal risk calculus. And to be fair, ENISA fully acknowledges this tension.
Okay.
Organizations are being forced to mathematically weigh two scenarios. Scenario A is that an automated patch might contain an error that causes system downtime.
Bad, but survivable.
Right. Scenario B is that leaving the vulnerability unpatched for even a few hours guarantees an AI-driven breach and total data loss.
Wow. So it's a choice between a potential IT headache and a guaranteed catastrophic breach.
Exactly. And ENISA notes that massive organizations, the ones with immense resources, they'll adapt to this.
How?
They can build highly sophisticated parallel environments where the AI instantly tests the patch on a digital twin of the network before applying it to the live server.
Okay, that makes sense.
But small and medium enterprises, SMEs, they simply do not have the resources or the infrastructure or the highly specialized skills required to build resilient, autonomous patching pipelines.
Yeah, they just don't have the budget for a digital twin.
No, not at all.
Which flows directly into the economic breakdown detailed in Structural Challenges 2 and 7.
Right.
I want to combine these two concepts for you guys because they really represent two sides of the exact same coin.
Yeah, they do.
Challenge 2 is the economic devaluation of discovery, and Challenge 7 is the flood of AI-generated vulnerability reports.
Because we are witnessing the rapid industrialization of bug hunting.
Yes.
Historically, finding a software vulnerability was an artisanal process. It was slow. Now, the marginal cost of discovering a flaw has plummeted effectively to zero.
Let's look at the specific example ENISA provides here, which really illustrates how thoroughly the system has broken down.
It's a crazy example.
It really is. So an industry representative shared their internal data regarding the volume of vulnerability reports they receive.
Okay.
A few years ago, a typical tech organization might receive, say, a few hundred reports annually from independent researchers.
Right.
And perhaps 100 of those would be legitimate enough to be assigned a formal CVE ID.
A common vulnerabilities and exposures tracking number. Yeah.
Exactly. So in the first quarter of 2025, this specific organization received about 80 CVEs.
Okay, totally manageable.
Right. But by the first quarter of 2026, just 12 months later, that number jumped to nearly 500.
Wow.
And then they applied frontier AI-enabled tools to their own internal scanning pipelines. And the volume didn't just double. It skyrocketed to 500 reports per day.
500 a day. I mean, you literally cannot hire enough human engineers to manually read, triage, verify, and write fixes for 500 complex vulnerability reports every single day.
It's impossible.
The entire global ecosystem of vulnerability disclosure relies on human coordination.
Right.
Security researchers find bugs, they submit them to platforms, humans verify them, and humans coordinate the fix. But by early 2026, this volume triggered a systemic crisis.
Yeah, the text actually mentions two high-profile casualties of this crisis, HackerOne and Curl.
Yeah.
Break down what happened there for us.
So, HackerOne is this massive global bug bounty platform where companies pay hackers to find flaws in their systems.
Right, very famous.
They actually had to pause new internet bug bounty submissions because the system was completely overwhelmed.
To shut it down.
Paused it, yeah. And then you have curl. For those who might not know, curl is a fundamental, ubiquitous piece of open source software.
It's in everything.
It is used in almost every connected device on the planet to transfer data. Well, in January 2026, the maintainers of curl entirely shut down their coordinated vulnerability disclosure program.
Wait, they just turned off the inbox, literally.
They did. Why? Because they were drowning in AI-generated noise.
Wow.
When these AI tools first became widely available, security researchers used them to automatically scan open source projects.
Sure.
But the AI would just generate massive dumps of theoretical attack
Oh, I
vectors.
see.
So the human reviewers maintaining curl were spending all their time trying to separate actual exploitable issues from repetitive, superficial AI hallucinations.
What a nightmare.
Yeah, the reporting pipeline devolved from a valuable discovery channel into just a massive triage bottleneck.
It's like running a post office where your security team traditionally screens, I don't know, 100 packages a day for contraband,
Right.
and suddenly an automated system drops 50,000 packages on your loading dock every morning.
Yes.
Even if the system claims it knows which ones are dangerous, you physically lack the human hands to open, inspect, and disarm them all before the end of the day.
Exactly. But, and this is crucial, ENISA points out a critical evolution that has occurred in just the last few months, leading up to July 2026.
Right.
The quality of these AI-generated vulnerability reports has vastly improved.
Wait, if the reports are getting better, doesn't that solve the problem? Like less hallucinations?
It actually makes the bottleneck worse,
How?
because it is no longer just a mountain of theoretical noise. There is now a massive influx of real, high-quality signal.
Oh.
The AI is finding legitimate, deeply complex vulnerabilities at an industrial scale.
Oh, wow.
And organizations still cannot process them fast enough because the limiting factor remains human reviewer capacity.
So the packages on the loading dock aren't false alarms anymore. They are real bombs, and they are still piling up faster than humans can defuse them.
Yes, and ENISA emphasizes that to survive this, organizations must aggressively adopt vulnerability prioritization mechanisms.
Okay, like what?
They specifically mention frameworks like the Exploit Prediction Scoring System, or EPSS, and the Vulnerability Exploitability Exchange, which is VEX.
Okay, explain how EPSS and VAGS actually function dynamically. How do they help filter the noise for you guys in the trenches?
So EPSS doesn't just look at how bad a vulnerability is in theory. It uses machine learning to predict the actual probability that a specific vulnerability will be exploited in the wild within the next 30 days.
Oh, so it gives you a real-world threat score.
Exactly.
Yeah.
And VEX is a machine-readable document that tells a user whether a specific product is actually affected by a known vulnerability.
How does that help with the speed issue?
Well, instead of a human reading a report and guessing if their system is exposed, automated systems ingest the VEX data and immediately deprioritize alerts for components that aren't actually active or exploitable in their specific environment.
That is brilliant.
It is. It's the only way to focus scarce human resources on what actually matters in a daily avalanche of 500 reports.
Wow, okay. This brings us to challenge 3. And this one is terrifying for any company that has been in business for more than like 5 years.
Oh yeah, technical debt.
Yes. Technical debt is an existential risk. We know AI can find new bugs and new code at light speed, but what happens when you point these frontier models at old legacy code?
It is a massacre.
A massacre.
Truly, legacy systems are built on decades-old assumptions about security.
Right.
AI-assisted analysis and reverse engineering tools can ingest massive amounts of archaic code, instantly understand the architecture, and discover fundamental flaws that human auditors missed for 20 years.
Wow. Because humans get bored reading millions of lines of outdated code, but an AI can parse it in seconds.
Exactly. Now, ENISA is careful to state that having a legacy system doesn't make it automatically undefendable.
Okay.
You can theoretically protect old code using intense system hardening, aggressive network segmentation, and hypervigilant security monitoring.
But the financial and operational cost of maintaining those defenses around an inherently flawed core, that is going to skyrocket, right?
Precisely. Technical debt, the backlog of known vulnerabilities, outdated dependencies, and deprecated systems, it transitions from being an IT annoyance into an existential business threat.
Wow.
ENISA suggests this transformational pressure will essentially force small and medium enterprises to abandon their on-premises legacy servers entirely.
So they won't be able to afford the bespoke security required to protect their old physical servers from ambient AI scanning.
They will have no choice but to migrate to modern, heavily defended cloud environments just to survive.
That makes sense.
Yeah, the major cloud providers have the scale to implement the autonomous patching and AI defenses we discussed. But an SME running a 10-year-old server in a closet, they simply cannot compete with the ambient radiation of autonomous AI discovery.
So if AI generating thousands of legitimate bug reports solves the discovery problem, it creates a terrifying new one.
Yes, it does.
Which ENISA details in Challenge 4, the verification bottleneck and the truth crisis.
This one is fascinating.
It really is. We established that AI can find the bugs and write the patches, and you said advanced models are incredibly good at reducing false positives.
Right.
But the sheer volume of true reports, accompanied by AI-generated patches, creates an epistemological crisis for engineering teams.
The truth crisis.
Yes. If a machine finds the bug and a machine writes the patch, but human developers still have to audit and validate that patch to ensure it doesn't introduce new vulnerabilities,
Right.
how do you actually trust the AI's homework? Like, what if the AI hallucinated a fix that accidentally or even intentionally, if the model was compromised, hides a backdoor?
And that is the verification bottleneck.
Yeah.
Technical teams face an impossible challenge of scale here. They are asked to manually verify highly complex code changes generated by machines at a rate they can't possibly keep up with.
It's just too much volume.
Way too much.
Yeah.
And to compound the issue, ENISA notes a shift in how we must treat low-risk vulnerabilities.
Okay, because in the past, if a bug was classified as low risk, say, it only allowed an attacker to see a directory name, but not access any files. It would go into the IT backlog.
Right, a ticket for later.
Yeah, maybe they'd patch it in 6 months if they had time.
Well, you can't do that anymore.
Why not?
Because of the AI's ability to chain vulnerabilities, which we discussed earlier.
Right.
The AI can take 3 seemingly harmless, low-risk misconfigurations and string them together to create a critical, system-compromising exploit.
Wow.
Therefore, every single patch, even for the most minor issues, must be verified and deployed immediately.
So the burden on the human verifier is astronomical.
It really is.
And here is where the ENISA document reveals perhaps the most insidious dynamic of all. Challenge 5. End-day weaponization.
This one is brutal.
It really is. Let's say you survive the verification bottleneck. You get the patch, you verify it, and the software vendor releases it to the public. You might think you're safe.
You'd hope so.
But the document explains that a public patch is essentially an instruction manual for an attacker's AI.
Yes. This revolves around a technique called patch diffing.
Okay, mechanically, how does patch diffing work, and how does AI change it?
So diffing is short for differencing. When a vendor releases a security update, they are pushing new, compiled binary code.
Okay.
Historically, highly skilled human reverse engineers would download the old, vulnerable version of the software and compare it side by side with the newly patched version.
Like spotting the differences in two pictures.
Exactly. And by finding the exact lines of code that were changed, they could reverse engineer what the original vulnerability was, how it functioned, and most importantly, how to build an exploit for it.
So the patch itself reveals the weakness.
Yes.
But for humans, reverse engineering compiled binaries, that took days or weeks of painstaking analysis, right?
It did. But now, Frontier AI can perform complex patch diffing instantaneously.
Wow. So the moment a vendor announces, we have released a critical security update, please download it, the attacker's AI downloads the patch, reverse engineers the fix, isolates the original flaw, and instantly generates a working exploit.
It turns the patch into a weapon.
That is terrifying.
It is. The AI then immediately begins scanning the internet and attacking any organization that hasn't clicked update yet.
Wow.
So the exploitation window doesn't begin when the vulnerability is secretly discovered. It begins the exact second the patch is publicly deployed.
Your exposure persists for whatever length of time it takes your organization to test and schedule the update.
Exactly.
And if you are an operator of essential services like a hospital, a power grid, a telecom provider, you can't always just reboot a critical system in the middle of a Tuesday afternoon.
No, you definitely can't, which is a massive vulnerability.
Right.
They are forced to invest in sophisticated, proactive security measures like dynamic web application firewalls and real-time behavioral monitoring just to defend the system while they wait for a safe window to apply the patch.
Which means the old way of building software, where you write the code, release it, and then fix the bugs later, is fundamentally dead.
Completely dead.
And that brings us to Challenge 6, the secure SDLC revolution. SDLC being the software development lifecycle.
Right. ENISA is calling for a mandatory shift toward a secure SDLC.
Okay.
We have to move away from a model based on finding bugs after the software is compiled and deployed. Security must be integrated directly into the development pipeline from day one.
So cybersecurity as code.
Exactly. The new paradigm is cybersecurity as code.
You cannot bolt security on at the end of the process anymore. It must be built into the architecture.
Yes. And this requires a massive focus on upskilling the existing workforce.
For sure.
Developers, integrators, and even end users, they need to understand how to detect vulnerabilities early in the design phase.
Right.
Particularly those vulnerabilities that arise not from bad code, but from the complex integration of various systems and configurations.
Speaking of complex integrations, we have to examine Challenge 8.
Ah, yes.
This is the final structural challenge ENISA outlines in this section, and it's called the risk of inside-out attacks. This concept completely inverts traditional threat modeling.
It really does, because traditional cybersecurity is obsessed with the perimeter.
Right. Firewalls.
Exactly. We build firewalls, secure gateways, VPNs. The traditional vulnerability exploitation paradigm assumes the attacker is standing outside the castle, trying to find a crack in the wall to get in.
But the attackers have realized that breaking the wall is too hard, so they are targeting the supply chain instead.
Yes. Adversaries are increasingly compromising the AI models and the software supply chains themselves.
Give us an example.
Well, if an attacker can compromise an open-source code library that your developers rely on, or if they can subtly poison the training data of an AI model your company uses for internal analytics, they don't need to breach your perimeter.
They arrive inside your infrastructure, hidden within a trusted, mathematically verified update.
Exactly.
They are already inside the castle walls.
And once they are inside, they only need to move laterally across the network to access sensitive databases and exfiltrate information.
This threat model means perimeter defenses are largely useless.
Mostly, yes.
I mean, if the call is coming from inside the house, locking the front door doesn't help you at all.
No, it doesn't.
You have to deploy detection and response strategies that operate on the absolute assumption that you are already compromised.
Always assume breach.
Yeah.
So, to summarize the syllabus so far,
Yes, let's review.
the exploit timeline has collapsed to minutes. Human authorization boards are too slow. Bug reporting has been industrialized into a flood of noise and signal. Patches are instantly weaponized against us. And attackers are starting from inside our networks via supply chain poisoning.
It is a really bleak picture.
It is.
Which leads perfectly into Section 4 of the ENISA document. Security fundamentals matter more than ever.
Now, this might sound counterintuitive to the listener.
Right.
With all of these revolutionary sci-fi AI threats, like autonomous patching, machine speed patch diffing, inside-out supply chain poisoning,
Yeah.
why is ENISA emphasizing basic fundamentals?
Because if your foundation is cracked, AI speed will simply shatter it faster.
Exactly.
Let's look at vulnerability management and incident response. We already established that autonomous patching is going to become effectively mandatory.
Yes.
But what happens when the patching fails and a breach actually occurs?
Well, incident response becomes a sprint against AI-orchestrated attack campaign.
A sprint.
Yeah. Security operations centers have to validate intrusions against live network telemetry, and they have to do it potentially within minutes.
Minutes.
And ENISA highlights a striking and frankly tragic statistic from the 2025 Palo Alto Network's Unit 42 Global Incident Response Report.
This statistic is the core of the human problem. What did the report find?
It found that in 75% of successful breaches, logging and telemetry actually existed that should have flagged the anomalous behavior to the defenders.
Wait, the alarms were functioning, the data was being recorded?
The data was there, but the signals were fragmented across dozens of different security tools.
Ah.
Human analysts missed the subtle correlations, or they simply suffered from alert fatigue and didn't act upon the data in time.
Tool fragmentation.
Yeah.
I mean, when human attackers took days or weeks to move laterally through a network, a human analyst had the time to manually cross-reference an alert from the firewall with an alert from the identity management system.
Right.
But at AI speed, that fragmentation is fatal. You physically cannot have an analyst cross-referencing 5 different dashboards manually.
No, you can't. To survive, service providers have to dramatically harden their operations.
Okay, how?
Risk assessments must evolve from static spreadsheets into dynamic processes that blend traditional event logging with runtime AI guards, automated access controls, and real-time threat intelligence sharing across the entire sector.
ENISA specifically points to their technical implementation guidance on NIS2 risk management to reinforce this.
Yes, they do.
What does NIS2 actually demand in practice?
So NIS2 is a sweeping European directive. It forces critical entities to operationalize their incident handling policies, mandate strict supply chain security, and actively engage in threat hunting rather than just waiting for alarms to go off.
Okay.
But ENISA warns that at a national level, this creates a massive bureaucratic bottleneck.
Right. NIS2 mandates strict incident reporting timelines.
Exactly.
If everyone is getting attacked faster due to AI, and everyone is legally required to report those incidents immediately, the national cyber agencies are going to be completely swamped.
Completely. ENISA warns of a severe structural risk here. Simultaneous surges in complex incidents that vastly exceed national response capacity.
Oh, wow.
Think about it. If a state-sponsored AI launches an attack that breaches 12 different power grids, telecom providers, and banks in the same hour, how does a national government prioritize its response?
They can't.
Right. So governments are being told they must integrate private industry into their crisis planning and establish robust surge capacity models immediately.
Let's shift from the networks to the products themselves. The text heavily emphasizes the CyberResilience Act, the CRA, and how manufacturers must adjust their product life cycles.
Yes.
They outline a very specific, fascinating requirement for the developers of AI models.
The CRA will require that developers of AI models train their systems to be structurally constrained.
Okay, structurally constrained.
And ENISA explicitly notes that a structural constraint is significantly stronger and more fundamental than a simple guardrail.
Okay, mechanically, what is the difference between a guardrail and a structural constraint for the folks building these things?
Good question. A guardrail is an external filter layered on top of an AI.
Like a safety net.
Exactly. The AI might generate a piece of malicious code, but the guardrail catches it before it is displayed to the user and says, I cannot fulfill this request.
Right, we've all seen those messages.
But guardrails can be bypassed through clever prompt engineering.
Sure.
A structural constraint means the underlying architecture and weights of the model are fundamentally designed and aligned so that it lacks the capability to generate that malicious output in the first place.
It's the difference between putting a muzzle on a dog versus breeding a dog that doesn't have teeth.
Exactly, yeah. Because, a muzzle can be taken off,
Right.
and developers must ensure these structurally constrained models exclusively suggest code that is secure by design and secure by default.
How do they prove that, though?
To actually prove this is happening, ENISA proposes the mandatory use of machine processable security attestations and software bill of materials, or SBOMs.
Okay, normally security compliance is a static PDF report sitting on a manager's desk.
Yeah.
But ENISA is saying these reports now need to be code. Explain how a dynamic SBOM functions.
Yeah, think of an SBOM as a highly detailed digital nutritional label for your software.
I like that analogy.
It doesn't just say Enterprise App version 2. It says, this application is composed of 20% open source library X, 10% dependency Y, and uses AI model Z.
Okay.
But it's not a static document. It is machine-readable code tagged directly to the software.
So if a new zero-day vulnerability drops for open source library X,
Right.
your network doesn't wait for a human to read a memo from the vendor.
Oh.
The network's defensive AI instantly scans the dynamic tags across the entire infrastructure, realizes which specific applications contain library X, and isolates them instantly.
Exactly. You embed threat modeling and least privilege access from the very outset of the product lifecycle, making the environment self-aware of its own composition.
All of this automation inevitably leads to a massive question regarding human capital.
The human element, yeah.
The ENISA document strictly mandates a cross-cutting principle. They say the human must be kept in the middle.
Yes. While AI will build systems faster and execute defenses autonomously, humans must maintain a deep architectural understanding of the environments they are legally and ethically responsible for.
Okay, if you are a listener sitting in IT, development, or security right now, what does your day-to-day actually look like in this new era?
It's a big shift.
Is your job shifting from being an active defender staring at logs and manually writing firewall rules to becoming essentially an AI wrangler?
Yes.
Yeah.
The required skill set is pivoting sharply and violently.
Violently.
You will no longer be fighting the individual viruses. You will be managing the immune system.
Wow, managing the immune system.
This requires raising the level of architectural awareness and strategic understanding across all levels of an organization. You need to understand how to guide, audit, and deploy defensive AI agents, and how to define the risk parameters under which they are allowed to operate autonomously.
Which brings us to the final and most actionable part of the ENISA document. Section 5, the way ahead building AI-resilient defenses.
The playbook?
This is the actual survival playbook. ENISA breaks these recommendations down into 3 tiers: the European level, national authorities, and finally, directives for defenders, which is the playbook for you, the listener. Let's start at the top.
Okay, so at the European level, the EU plans to leverage their existing and upcoming legal frameworks aggressively.
Makes sense.
This includes the CyberResilience Act, the NIS2 Directive, and crucially, the AI Act. Specifically, Article 55, which deals with identifying and mitigating systemic risks arising from advanced general-purpose AI models.
So they want to establish standardized EU-wide benchmarks for evaluating the security of these massive models,
Right. Yeah.
including measuring their exploitability and their ability to conduct simulated chained attacks.
Right. But the most ambitious proposal at the European level revolves around data.
Data.
Yeah. European institutions, national computer emergency response teams, CSIRTs regulators, and critical infrastructure operators collectively sit on a staggering mountain of cybersecurity data.
Oh, like incident reports and stuff.
Incident reports, vulnerability disclosures, real-time telemetry, and malware samples.
So ENISA is arguing that, subject to strict anonymization and privacy safeguards, obviously, this data shouldn't just be archived in filing cabinets.
Right.
It must become a strategic asset.
Yes. They propose pooling this massive continental data set to train, evaluate, and continuously fine-tune defensive EU-based AI models.
Oh, that's smart.
The goal is to create trusted, sovereign European cyber AI models that possess a deep native understanding of the unique infrastructure, regulations, and threat landscape of the continent.
Moving one tier down, what are the marching orders for national authorities?
National governments are directed to run continuous AI-powered threat hunting operations across their critical sectors.
Okay.
They are also tasked with publishing anonymized data sets derived from frontier AI attack simulations to help the private sector train their defenses.
Giving back to the community.
Exactly. Furthermore, they must mandate that critical infrastructure operators legally attest to maintaining zero-trust baselines during their annual audits.
And they have to build that surge capacity we discussed earlier.
Yes.
They need defined, pre-authorized escalation paths for when AI-accelerated incidents inevitably overwhelm normal bureaucratic channels. ENISA also explicitly directs national agencies to abandon ineffective legacy security tooling.
Yeah, they must complement their national security stacks with AI-enabled platforms that are actually capable of ingesting and correlating threat data in real time, matching the speed of the autonomous attackers.
Now we arrive at the most critical part of this deep dive.
There we go.
The directives for defenders. If you are a CISO, a security architect, or an IT director, this is your immediate playbook. Let's walk through these final recommendations.
All right, Directive 1. Assume you are already breached.
Always.
You must treat every environment as potentially compromised from the inside out. To counter this, you must deploy real-time machine learning-based prevention and detection on all on-premises servers and cloud hosts.
And the text specifically calls out a fascinating new attack surface, securing agentic endpoints in enterprise browsers.
This is a huge one.
Why are enterprise browsers suddenly a critical battleground?
Because the nature of work has shifted into the browser, and so has the AI.
Oh, right.
We are seeing the rise of agentic endpoints. These are AI agents that operate autonomously directly on used laptops and within web browsers to perform tasks, scrape data, or manage workflows.
Right.
If an attacker compromises the browser, they compromise the AI agent operating within it, gaining direct access to the enterprise's SaaS applications and authenticated sessions.
Wow.
So you can't just protect the backend server anymore. You have to lock down the very browser the AI is using to interact with the world.
Directive 2. Continuous red teaming. This is where the defense actually gets exciting.
It is a radical shift in posture.
How so?
Organizations must embed structured threat modeling continuously. You are directed to leverage advanced AI models to uncover combinations of weaknesses against your live architectures.
You are essentially taking the attacker's weapon and turning it into an always-on immune system. You deploy an autonomous, friendly AI that constantly, 24/7, tries to hack your own company, finding the flaws and fixing them before the malicious AI finds them.
Exactly. Directive 3. Dynamic incident response pipelines.
Okay.
You must use AI-assisted triage for real-time telemetry validation. And crucially, you must empower the AI to execute blast radius containment.
Explain blast radius containment in this context.
If the defensive AI detects that a server has been breached, it does not wait for a human analyst to wake up, review the logs, and authorize a shutdown.
Right.
The AI instantly, autonomously isolates that specific server from the rest of the network, containing the blast radius of the attack to prevent lateral
Or
movement.
just cuts it off.
Yes. It does this while keeping human review firmly in the loop to manage the broader crisis and to meet mandatory 24-hour legal notification requirements.
Which leads to the final directive, a metric that perfectly summarizes the total collapse of time we have been discussing since the very beginning of this deep dive.
Single-digit minutes.
Yes. Target single-digit minute mean time to detect, MTTD, and mean time to respond, MTTR.
You must transform your security operations into a near real-time function.
Minutes, not hours.
You have to accelerate zero-trust segmentation and deploy evasion-resistant detection layers, operating on the foundational assumption that attackers will adapt and evolve their tactics in near real time.
Single-digit minutes. That is the new, non-negotiable gold standard for organizational survival.
It is.
We have covered an immense amount of ground in this walkthrough. We have journeyed from the terrifying reality of a 15-minute weaponization window through the necessary death of human speed patching and change advisory boards,
Right.
to the sheer necessity of autonomous AI-integrated defenses and continuous machine speed red teaming.
It really represents a profound, permanent shift in how we must conceptualize digital trust, architecture, and defense.
Before we wrap up this deep dive, I want to leave you with a final thought to mull over, building on the underlying philosophy of this ENISA text.
I love this part.
If attackers are using autonomous AI to write exploits, and defenders are forced to use autonomous AI to patch those vulnerabilities and contain the blast radius, cybersecurity essentially transforms into a hyperspeed, machine-to-machine immune system response happening silently in the background of our networks.
Yeah, if the code is writing, attacking, identifying, and fixing itself in milliseconds, entirely outside the loop of human cognitive speed, does the future of human cybersecurity ultimately become less about writing code and entirely about designing the risk appetites, the architectural constraints, and the rules of engagement of our AI proxies?
Exactly. Are human CISOs eventually just generals pointing autonomous armies of algorithms at each other?
It's a question that completely redefines the profession.
It really does. For now, the takeaway is clear. Go review your own organization's mean time to respond. Are you measuring your response in days, hours, or those crucial single-digit minutes? We invite you to join us for our next deep dive as we continue to explore the bleeding edge of technology and security. Until then, stay secure.